In the first of our video lectures on energy, I will briefly review the idea of work that we dealt with in the last lecture, and I'll do several simple examples. The work done is described by a mathematical relationship. It is the component of the force in the direction of the displacement. So the work done is equal to the force times the displacement times the cosine of the angle. The angle is measured from the x-axis in an anti-clockwise direction. This work is equal to force times displacement times cosine of the angle is a scalar product. That means that the result of this calculation does not have a direction associated with it, only a magnitude. And it is also can be written down as something known as a scalar product, and that is something we will deal with in this series of video lectures, what a scalar product is. The unit of work is a joule, and 1 joule is the amount of work done when a force of 1 Newton is applied over a distance of 1 metre. So we're using energy-based solutions to deal with situations that can be quite complex, especially those where the force, and therefore the acceleration, is not constant. And to do this, we'll end up with the work-energy theorem. But first of all, we need to be able to understand how simple calculations for work can be done. So the first example that I'll look at is how much work is done by the normal force in this case. So we're dragging this block across a surface, and the normal force is at right angles to the surface, as seen in this diagram. Now, if we look at the angle between the horizontal and the normal force, it's 90 degrees. All right, so if that is 90 degrees, then the work done by the normal force is equal to the value of the normal force times the displacement times the cosine of 90 degrees, which is 0. So 0 work done is done by the normal force in this example. You'll also notice that 0 work will be done by the gravitational force. So the only work done in this example is that done by the pushing or pulling force, labelled F. So let's have a look at this situation. So we're pulling a bag along. It's basically just a slightly more real-world example of the block example I had in the previous slide. We're pulling along our suitcase, applying a force, as you can see, and we move some displacement S. So during that time, we're dealing with a constant force, all right, and we can have a look at the displacement. So the first step in that is to look at the difference between various orientations of the suitcase. So if cosine of 0, if the angle was 0, then cosine of 0 would be equal to 1, and the work would just be equal to force times displacement. If the angle is 90 degrees, then the work done is 0, the work done by that force in the direction of displacement. And if cosine is equal to minus 1, if we look at 180 degrees, then cosine of 180 is equal to minus 1. So first of all, the work done by the force is 45 newtons, the angle with the horizontal is 45 degrees, and the displacement is 75 meters. We're clearly in an airport. So we can substitute those values in straight off. The force is 45 newtons, the angle is 50 degrees, and the displacement is 75 meters. So 2,170 joules of work have been done by the person on the bag in moving it a distance 75 meters. Now, if we look at the situation for a weightlifter, for example, and they're moving the weights vertically up or down. So as the weightlifter rises, the weightlifter applies a force in the positive y direction, and the displacement is in the positive y direction. So the work done will just be F times S, since the angle is 0 and the value is positive. Now, as the weightlifter lowers the weight, right, and lowers it so that so he doesn't kill himself, basically, he'll be applying a force upwards still, right, basically to balance the effect of gravity, but the displacement will be downwards. So the product of the force he applies and the displacement gives us a negative work. So as the weight is lowered, negative work is done by the weightlifter on the weight. And remember, in all of these cases, we have to carefully consider what is the agent and which is the object. We're always looking at what the agent does to the object. So here's our first multiple choice question. We've got 4 situations in which the force is applied to an object. In all 4 cases, the force has the same magnitude, and the displacement is to the right and of the same magnitude. You need to rank the situations in order of the work done by the force on the object from the most positive to the most negative. Now, this situation can get quite complex because you'll notice that we're actually dealing with a vector multiplication. We've got forces and displacements and angles, and that means both magnitude and direction come into the way the problem is stated. However, the answer that we get is a scalar product. It has no direction. It has just got a magnitude. So that brings us to dealing with how do we multiply vectors. It turns out there are 2 types of multiplication for vectors. One is called the scalar or dot product, and that is a multiplication of vectors that gives us a scalar result. The second way to multiply vectors is called the vector or cross product, and that gives us a method that gives us a vector result. To begin with, I'm going to talk only about the scalar product. So the scalar product for 2 vectors, A and B, is shown on this diagram. We know from the way we defined work that the scalar product of a work was F times displacement times the cosine of the angle. For any 2 general vectors, then the scalar product A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. This is known as the dot product. And the scalar product obeys the rules that you know for arithmetic. It doesn't matter what order you do your calculation. You can find the scalar product of A and B or the scalar product of B and A. This is not true when we deal with the vector product. The scalar product also obeys the distributive law of multiplication. So you could add B and C first of all, and then find the scalar product of A with that result. Or you could multiply it out and go A dot B plus A dot C. And so in these processes, these behave just like your normal arithmetic does. However, there is also a way of defining this scalar product in terms of these unit vectors that we've dealt with. If you remember, the unit vector I was 1 unit along the x direction, the unit vector j was 1 unit along the y direction, and the unit vector k was 1 unit along the z direction. So if we found the various scalar products associated with unit vectors, right, we could take that vector notation and use it to create a scalar product. So that's what we'll do. There's this property called the orthonormal property. It means that if the 2 vectors are at right angles, the cosine of the angle is 90 degrees, then the scalar product is 0. So if we take I and j, the unit vector along the x-axis and the unit vector along the y-axis, then I dot j, the scalar product, will equal 0. And you'll see the other combinations that are at right angles to each other, I and k, j and k, each give 0 for the scalar product. So when we multiply these vectors, we'll end up with 0. However, if we're looking at parallel vectors, so that the angle is 0, for example I dot I, we get I dot I is equal to 1. Each of those i's has a unit magnitude and the angle between them is 0. So I dot I, j dot j and k dot k are all equal to 1. And that means that if we go through our normal mathematical process for doing this, then we can find a result for A dot B in terms of the components of the vector. Alright, so if we take A, which is an x component, a y component and a z component, and a B, which also has an x, y and z component, we can end up with the scalar product being equal to the product AX times BX plus AY times BY plus AZ times BZ. Now, I will provide another document that shows how this explicitly comes about from these orthonormal properties. But for now, the most important thing I can tell you is that if you are given the components of two vectors, you are able to simply calculate the scalar product using this equation. A dot B is equal to AX times BX plus AY times BY plus AZ times BZ. Note that there is no I, J or K vector involved in this. This is the end result of this is a number. All right. It is a scalar, it is the scalar product, and you will be given this formula explicitly on your formula sheet for any quiz or exam associated with this. And as far as I know, there's no way to remember this easily. There is a way to calculate it, but I don't expect you to do that. You need to be able to use this form of the scalar product. You need to be able to use both. The scalar product is AB cosine of theta, and you need to be able to express it in terms of these components. Why? Well, it turns out that in physics and engineering and other fields, scalar products come up a lot. We've already dealt with work. The work done on an object is the scalar product of a force and a displacement. The power is the scalar product of a force and a velocity. And there's a thing in magnetism called the magnetic flux, which you will come across, which is the scalar product of the magnetic field and the area of a loop. Each of these will be discussed later, but you should look at the index in your text and find out what they are and what they mean. So let's summarize what we've got. Scalar products arise throughout physics, especially when we deal with energy. The basic definition of a scalar product is A dot B is equal to magnitude of A times magnitude of B times cosine of theta. This is essentially a geometric definition, and for those of you who have done some more advanced trigonometry, this is directly related to what is known as the cosine rule. So we're coming back to force. We're coming back to the work done. The work done is the scalar product of the force and the displacement, F r cosine theta. And if the displacement is normal to the force, then no work is done. But let's have a look at a specific example using vectors to work out the scalar product. We want to find the work done in moving an object along a vector equal to 3i plus 2j minus 5k with due to a force of 2i minus j minus k. So the work done is equal to the magnitude of the force in direction of motion times the distance moved, or F cosine of theta times r, or the scalar product of force and displacement. And that's definition that we are going to use to do this calculation. So we have 2i minus j minus k dot 3i plus 2j minus 5k. And if you refer back to the formula I had earlier, we have ax times bx, 2 times 3 is equal to 6, plus ay times by minus 1 times 2 minus 2, plus az times bz minus 1 times minus 5 plus 5. 6 minus 2 plus 5 is equal to 9 joules. There is no direction involved in this.